Hello and welcome to Slow Orbit. Before we journey deeper into the vastness of the universe, take a moment to like and subscribe so you don't miss any of our cosmic explorations. And while you're here, I'd love to know, where are you watching or listening from? Are you tuning in from a bustling city or perhaps a quiet corner of the world? Wherever you are, it's fascinating to think that, no matter the distance, we're all looking up at the same infinite sky. Or are we? Today, we're diving into a question that has captivated humanity for centuries. Where does space end? Is it infinite, stretching on forever, or does it have a boundary, a limit? We'll explore the ideas of visionary scientists, dive into complex theories, and ponder the very fabric of the universe itself. So sit back, relax, and prepare for a journey that takes us far beyond our familiar world to the edges of space and beyond. Hello, and welcome to Slow Orbit. Today we're starting with a simple yet mind-bending question. Where does space end? Is there a boundary to it? Or, as many wonder, is space infinite, stretching out endlessly, forever? This question, while intriguing, isn't just something that people have been pondering in recent years. It goes back hundreds, even thousands of years, rooted in the very essence of our curiosity about the universe. Humans have always looked up at the stars, wondering if there's an end to it all. The first philosophers and thinkers tried to grapple with the very nature of space itself. Some thought the universe was a finite, ordered place with clear boundaries. Others, however, looked deeper, suspecting that there might be no limits at all. This pursuit of understanding has shaped modern science and cosmology in ways that are at times difficult to grasp, but endlessly fascinating. Take René Descartes, the famous 17th century philosopher. Descartes had a rather unusual take on space. He didn't think that space itself had any inherent boundaries. Instead, he proposed that space was something absolute, not limited or confined by any physical structures. In his view, the universe could stretch on infinitely, with no real edge or end in sight. He considered space to be the container of everything, but it wasn't something that could be bounded or contained by anything else. Fast forward a few hundred years, and you find thinkers like Peter Strawson, a 20th century philosopher who took the concept of space to another level. He argued that our conventional understanding of space was simply too limiting. In his view, there was no definitive boundary to space because space itself wasn't something that could just be boxed in or defined in familiar terms. In his writings, he suggested that in fact the very notion of space having a boundary was a human invention, and that we might be asking the wrong kind of questions about it altogether. Space, for Strawson, was a more abstract, less tangible concept than we typically give it credit for. Both Descartes and Strawson, though centuries apart, had the shared notion that space wasn't something with edges or ends. But what they offered was far more philosophical than scientific. Their ideas were based on thinking beyond the confines of physical observation, something that, in the realm of modern science, would take on much more detailed and intricate forms. Let's shift now to the modern era of cosmology. Today, we no longer just look up at the sky with wonder and ponder what we see. We have the tools, the technology, and the theories to study the universe in ways previous generations could never have imagined. Edwin Hubble, for example, in the 1920s, revealed that the universe was expanding. What does this tell us? If the universe is expanding, that would mean that space itself is stretching, getting larger with every passing moment. This was a radical departure from the previous belief that space was static, something fixed. The discovery of this expansion meant that, at least in some sense, there could be no definitive end to the universe, as the edges of space would be moving farther away all the time. Now this brings us to the idea of cosmic inflation, an incredibly important theory introduced by Alan Guth in the 1980s. He proposed that in the very early moments of the universe, it expanded exponentially, at an unimaginable rate, far faster than the speed of light. During this period, space itself didn't just stretch. It stretched so rapidly that any edge or boundary of the universe was, for all practical purposes, wiped out. If the universe expanded like this early on, it could have effectively removed any possibility of a real boundary. And it's not just inflation that has altered our views about space. We've also developed ideas such as the multiverse, the theory that our universe might just be one of many, existing in parallel or even branching out into countless variations. In this framework, space might not only be infinite, it could also be part of a much larger, much stranger cosmic structure. This challenges us to rethink the very concept of space having limits. In the multiverse, the idea of edges becomes irrelevant because each universe could be entirely separate, with its own dimensions and physical laws. But it's not all just abstract theory. There are real observations that suggest the universe may indeed be infinite, or at least vastly larger than what we can observe. The observable universe is the portion of the universe that we can see and measure. The key here is that we can only observe what light has had time to reach us. This means that the observable universe has a boundary, but it doesn't necessarily represent the true limits of space. The further out we look, the farther we can observe, but there's no reason to assume that what lies beyond that is any different than what we already see. Could the universe simply keep going, forever expanding, just beyond the reach of our instruments? In this video, we'll explore these ideas and more, diving into the current theories that push the boundaries of what we think we know. From the mind-bending concept of an infinite universe to theories of multiple universes, we'll consider every possibility. We'll look at the discoveries that have shaped our understanding of the cosmos and explore some of the more unconventional ideas that have challenged our perceptions of space and time. So, as we embark on this journey, I invite you to keep an open mind. The universe might be far stranger than we could ever imagine, and the question of where space ends might just be the start of a much larger mystery. Let's explore together. The observable universe is vast, far beyond anything most of us can truly fathom. It's estimated to be about 93 billion light-years across. Now, that number is mind-boggling, isn't it? But what does it really mean? A light-year, after all, isn't just some arbitrary number. It's the distance that light travels in 1 year. And light, travelling at nearly 300,000 kilometers per second, covers an incredible distance. In 1 year, light can travel almost 9.5 trillion kilometers. That's nearly 63,000 times the distance from Earth to the Sun. So when we say the observable universe spans about 93 billion light-years, what we're really saying is that the space we can observe reaches out to a staggering 93 billion times that distance. But here's the tricky part. When we talk about the observable universe, we're talking about only what we can see, and that's only a tiny fraction of the total universe. The observable universe has a boundary, not because space itself has an edge, but because light from anything farther away hasn't had time to reach us yet. You see, space itself is expanding, and that expansion is happening at an accelerating rate. The farther away something is, the faster it moves away from us. So, even if light travels at its top speed, there are regions of space that are moving away so quickly that their light will never reach us. And as the universe continues to expand, these regions move farther and farther beyond our reach. This concept, that the observable universe has limits but that space itself may extend beyond them, is something that was difficult for scientists to accept at first. After all, the idea of an infinite universe doesn't seem to make sense. How could anything be infinite? But when you really start to think about it, the more you learn about space, the more the idea of an infinite universe becomes a valid, if strange, possibility. One of the key figures who changed the way we think about the universe's vastness was Edwin Hubble. In the 1920s, Hubble made a discovery that revolutionized our understanding of the cosmos. He found that galaxies were moving away from us, and the farther they were, the faster they seemed to be receding. This observation led to what we now know as Hubble's law. Essentially, Hubble showed that the universe is expanding, and that's a critical point. It's not that galaxies are moving through space as if space is empty, and they're just speeding along. No, space itself is expanding, stretching out like an inflating balloon. Everything is getting farther apart as the universe continues to grow. Now, when we talk about the expanding universe, it's important to note that we're not talking about the universe expanding into something else, like a balloon inflating into an empty room. Space itself is stretching, so the galaxies aren't moving through space, they're just getting carried along with it as space itself gets larger. Think of it like a raisin in a loaf of bread that's baking. As the bread rises, the raisin gets farther from all the other raisins, but the raisin isn't moving on its own, it's the bread that's expanding, and the raisin is just being carried along with it. What does this mean for the idea of boundaries? Well, it complicates it. Space itself doesn't have an edge. It's expanding all the time, and as it does, it stretches out farther and farther. That's why when we talk about the observable universe, we have to keep in mind that we're seeing just a slice of it. what we can detect based on how far light has had time to travel. The universe may be far, far larger than what we can measure. The observable universe is just what we can see now, not what exists in total. But what about the edge? Does the universe have an edge? If space is expanding, is there a point where it just ends, or does it go on forever? Well, that's where things get even more curious. Some scientists suggest that the universe might be infinite in size, with no edge or boundary at all. This would mean that if you were to travel far enough in one direction, you would never encounter an end. Instead, you would simply keep going, and space would keep stretching with you, endlessly. But we can't prove that just yet, because we've only been able to measure a small part of the universe, the observable portion. Still, the idea of an infinite universe is something many scientists consider plausible, especially given the way space continues to expand. When we talk about the vastness of the universe, the role of light years becomes crucial. As you might imagine, light years are an essential unit of measurement in cosmology. They allow us to grasp just how far apart things are on cosmic scales. The farther something is, the longer it takes for its light to reach us, and the more time we have to learn about the universe's history. Light from distant stars and galaxies shows us what the universe looked like in the past, sometimes billions of years ago. When we look at distant galaxies, we're seeing them as they were when the light first left them, long before humans ever gazed at the stars. This brings us to the idea of the cosmic horizon. This horizon represents the furthest distance from which light has had time to reach us since the beginning of the universe. Anything beyond this cosmic horizon is effectively unreachable, at least for now. In a sense, it's the limit of our view, the edge of our observable universe. And yet this edge isn't really an edge at all. It's simply the farthest distance that light, travelling at a finite speed, can have reached us. Space itself might stretch far beyond it, but we'll never know for sure with our current instruments. It's an incredible thought, isn't it? That the universe could be vastly larger than what we can observe, and that our view of the cosmos is just a small window into an even grander, more mysterious reality. As we continue to expand our understanding, with tools like the James Webb Space Telescope offering glimpses into the deeper universe, we can only imagine how much more we will learn in the future. But one thing is clear. The universe is far more vast and complicated than we ever thought possible, and its true size is likely much larger than what we can even comprehend. Imagine for a moment that you're looking out at the night sky. Stars, galaxies, nebulae, and distant clusters of light fill your view. Each of these objects exists far beyond the reach of our everyday experiences, but there's a limit to how far we can see, how far we can observe. This is where the idea of cosmic horizons comes in. It's a concept that helps define the boundaries of our observations in the universe. The observable universe, as we've discussed, has its limits, defined by how far light can travel over time. The concept of the cosmic horizon refers to the farthest distance from which light has had time to reach us since the beginning of the universe. In other words, the cosmic horizon represents the limit of what we can see, and it's constantly expanding as light from more distant objects travels toward us. But there's more to this idea than just seeing the furthest reaches of space. There's another type of cosmic horizon, known as the event horizon, which has its own implications for our understanding of the universe. The event horizon is a boundary, but it's not like the edge of the observable universe. The event horizon is a concept from general relativity that applies to black holes. It's the point beyond which nothing, not even light, can escape the intense gravitational pull of a black hole. Imagine this. As you get closer to the event horizon, the escape velocity, the speed you'd need to reach to escape the black hole, becomes greater than the speed of light. And beyond this point, no matter how hard you try, nothing can get out. It's a one-way boundary, drawing everything in without exception. This might sound like something that only happens inside black holes, but the concept itself is incredibly useful for understanding the nature of space, time, and even the limits of the observable universe. So while the observable universe represents the limits of what we can see, the event horizon, in a way, is the ultimate boundary, at least for anything that falls within a black hole's reach. But here's where things get interesting. The universe itself is expanding, and as it does, the distance between galaxies is stretching farther and farther, and this expansion affects our understanding of cosmic horizons. What makes this particularly fascinating is that the expansion of space itself can cause objects to move away from us faster than the speed of light. But we know that nothing can travel faster than light, right? So how does that work? It's all about the nature of space itself. The universe isn't just a static collection of stars and galaxies, it's a dynamic system, constantly evolving. Alan Guth's theory of cosmic inflation, proposed in the 1980s, explains how the universe underwent an incredibly rapid expansion in the moments right after the Big Bang. In a fraction of a second, the universe expanded by a huge factor, much faster than the speed of light. This inflationary period smoothed out the universe and set the stage for the large-scale structure we observe today. What's important here is that this rapid expansion was not about objects moving through space. It was space itself that was expanding. This idea is a game-changer when it comes to thinking about the limits of the universe. As space continues to expand, galaxies get farther apart and the space between them grows. But since space itself is stretching, some distant objects are receding from us at a rate faster than the speed of light. Does that mean that light from these objects can never reach us? In a sense, yes. Light emitted by these distant galaxies may never have the chance to catch up with the expansion of space. As the universe continues to grow, regions beyond a certain point will remain forever out of our observational reach. This is where the concept of a cosmic horizon comes into play once again. The farther away something is, the faster it moves away from us, and beyond a certain distance it's effectively unreachable. These horizons aren't edges. They're more like boundaries of influence, beyond which we can no longer receive information. They limit our ability to observe the universe, but they do not represent a physical edge to space itself. This understanding of the expanding universe presents us with a profound realization. Space, in some ways, might have no true end or boundary. Instead, it stretches endlessly, with parts of it moving farther away at speeds we can't keep up with. The universe itself might be infinite, expanding forever, and any attempt to reach the end of space is thwarted by the very nature of its expansion. And as the universe continues to stretch out, it's possible that we're only seeing a tiny slice of a much larger reality. Now, let's consider general relativity and how it shapes our view of cosmic horizons. Albert Einstein's theory of general relativity tells us that space and time are intertwined, forming a four-dimensional fabric called space-time. The curvature of this fabric, caused by massive objects like stars, planets, and black holes, shapes the way we experience gravity and how we observe the universe. This curved space-time is what allows for the concept of event horizons. Black holes aren't just objects that pull in matter, they warp the very fabric of space-time itself. The expansion of the universe too is governed by this dynamic fabric of space-time. As space stretches, it reshapes the distances between galaxies, and the speed at which space expands depends on the amount of energy and matter within it. This is where things start to get a bit mind-bending. The boundaries that we think we understand, like the edge of the observable universe, are really just a result of the limitations of space-time itself. The universe may very well be infinite, and if that's the case, there's no physical boundary, no edge in the traditional sense. But there's more to this. Even though we can't reach the edge of space, the expansion of the universe gives us a way to measure how far things are. It's not that we can never reach certain distant galaxies. They might simply be too far for us to ever observe, as their light will never catch up with the expanding space between us. But that doesn't mean that the universe has a physical limit. The real barrier we face is the cosmic horizon, and the expansion of space is the force that keeps pushing it farther away from us. These cosmic horizons, whether they're the limits of what we can see or the boundaries of what we can influence, represent the most distant reaches of the universe. But they are not true edges. They are boundaries of observation and influence, limits imposed not by some physical wall, but by the nature of space-time itself, which is constantly stretching and evolving. It's as if the universe is always just out of reach, ever expanding, yet always offering more to discover, more to explore, if only we could stretch far enough to see it. In the end, the question of whether space has an edge might be one that doesn't have a simple answer. It's not about finding a physical boundary. Rather, it's about understanding the dynamic, ever-expanding nature of the universe, and the limits of our ability to observe it. What lies beyond our cosmic horizon? Well, that's a mystery, one that may remain unanswered for as long as the universe continues to expand. But that's what makes the journey of discovery so exciting. There's always more to learn, more to explore, and more to wonder about. When we think about the shape of the universe, it's easy to imagine something simple, maybe a ball or a flat sheet stretching out in all directions. But as it turns out, the actual shape of the universe is far more mysterious and complex than most of us could have ever anticipated. Cosmologists have explored several different models to describe how the universe might be structured, and each of these models challenges our most fundamental ideas about space itself. One of the earliest and simplest ideas is the flat universe. This model suggests that space is flat in the sense that parallel lines never meet, and the angles of a triangle always add up to 180 degrees, just as they do on a flat sheet of paper. It's a model that makes sense in our everyday world, where we're accustomed to seeing straight lines and flat surfaces. In this model, the universe extends infinitely in all directions with no curvature, just an endless stretch of space. This kind of universe is the basis of many of our everyday intuitions about space, stable, unchanging, and boundless in all directions. But not all models of the universe are that straightforward. The spherical model of the universe is another possibility, and it suggests something much stranger. Imagine the surface of a sphere, like the Earth. If you travel far enough in one direction, you'd eventually end up back where you started, having circled the entire surface. If the universe was spherical in nature, it would be finite but unbounded, meaning that there is a limit to its size but no edge where things suddenly stop. In this model, the universe curves back on itself in a way that's difficult to visualize but still mathematically plausible. It's like walking in a straight line on the surface of a globe. You may never encounter a true boundary, but you are confined to the shape of the sphere. Then there's the hyperbolic model, which is yet another way the universe could be structured. In this model, space is curved in a way that's different from both flat and spherical models. Instead of space curving inwards or remaining completely flat, it curves outward, creating a shape known as a hyperbolic space. This kind of geometry is hard to wrap your mind around because it's so far removed from our usual experience of space. But in a hyperbolic universe, the rules of geometry shift. For example, the angles of a triangle would add up to less than 180 degrees. This model suggests that space could be infinite and unbounded, but shaped in a way that we don't encounter in our day-to-day lives. Now, imagine moving beyond these traditional shapes into more speculative territory, where the very fabric of the universe becomes even more dynamic. One of the most intriguing ideas comes from the ekpyrotic universe theory, proposed by Paul Steinhardt and Neil Turok in the early 21st century. This theory suggests that the universe is cyclic, meaning that it doesn't have a single, defining beginning or end. Instead, the universe goes through endless cycles of creation and destruction. The ekpyrotic model posits that the universe's birth is the result of a collision between two higher dimensional branes. Think of them as layers of space-time that exist in higher dimensions. These branes collide, causing the Big Bang and creating our universe. When one cycle ends, another begins, leading to an infinite sequence of cycles. In this model, there's no clear boundary to the universe, just a continuous, ever-repeating process that stretches across time in a cyclical pattern. It's a truly mind-bending way of looking at the universe, where time itself loops back on itself, much like a never-ending cycle. This idea challenges the very notion of a beginning or an end. In this cyclic view, there is no absolute edge to the universe. Instead, the universe goes through periods of expansion and contraction, never reaching a final boundary, but continually evolving in a way that's difficult for us to conceptualize. The implications of this model suggest that the universe could be far more fluid and adaptable than we originally thought, potentially going through infinite cycles of birth, death, and rebirth. And then there's the work of Roger Penrose, one of the most brilliant theoretical physicists of our time, whose ideas about the structure of the universe challenge our conventional understanding even further. Penrose suggests that the universe might be a smooth continuum, a unified whole where time and space loop back on themselves. His work on the conformal cyclic cosmology theory proposes that the universe is, in a sense, self-renewing. In Penrose's view, after each cycle of the universe ends, it is followed by a new one, with no true boundary or edge. The end of one universe becomes the starting point for the next, like a continuous smooth flow of space-time that never truly ends. This vision of the universe fundamentally alters how we think about space, suggesting that our current understanding of time and space is just a limited perspective on a much more complex cyclical reality. But if that's not enough to stretch the imagination, there's Max Tegmark's mathematical universe hypothesis, which is even more radical in its implications. Tegmark, a theoretical physicist at the Massachusetts Institute of Technology, suggests that the universe is not merely a physical structure, it's an abstract mathematical entity. According to Tegmark, everything in the universe, including space itself, can be described by mathematical structures. In his view, the universe doesn't have physical boundaries or edges in the way we usually think about them. Instead, it's a collection of mathematical structures that describe reality, and these structures extend indefinitely, meaning that the universe itself may not have any true physical form. The universe, in this sense, is entirely abstract, a vast mathematical construct that we only experience in physical terms because of our limited perspective. In a way, this challenges the very nature of reality as we know it, proposing that space and time are simply manifestations of a deeper mathematical reality. Each of these models, the flat universe, the spherical universe, the hyperbolic universe, the cyclic universe, and the mathematical universe, offers a unique perspective on the shape of space. But none of them are entirely settled. They each pose their own set of questions and challenges, and the more we learn about the universe, the more we realize just how little we actually know. Perhaps space is flat, or maybe it's curved in ways we can't yet perceive. It could even be infinite, stretching out in all directions without a true boundary. Or maybe, as some theorists suggest, space is something entirely abstract, a mathematical construct beyond our everyday experience. As we continue to explore these possibilities, one thing becomes clear. The shape of the universe is not something we can easily define or comprehend. It's a puzzle that, like the universe itself, keeps expanding the boundaries of our understanding, and as our tools improve and our theories evolve, perhaps one day we'll discover more about the true structure of space, unlocking secrets that have eluded us for centuries. Until then, we can only continue to explore the many fascinating models that defy the ordinary and stretch the limits of imagination. In the early 20th century, a revolutionary theory changed everything we thought we knew about space and time. This theory, developed by Albert Einstein, is known as general relativity. It challenged the way we viewed the universe, offering a whole new framework for understanding the very fabric of reality. The consequences of general relativity were profound and continue to shape modern physics today, particularly in how we understand the concept of curvature in space-time. At the heart of general relativity is the idea that space and time are not separate entities, but are woven together into a single, unified fabric known as space-time. This fabric is not flat as once thought, but can be curved or distorted by the presence of mass and energy. This concept can be a bit tricky to wrap your head around, but it's important to understand because it fundamentally changes our view of the universe. Imagine space-time like a stretched-out rubber sheet. When you place a heavy object, like a planet or a star, onto this sheet, it causes the fabric to bend and curve around it. This curvature is what we experience as gravity. Objects like planets or light follow the curves in this fabric, which is why they appear to be attracted to massive objects like stars or black holes. Before Einstein, gravity was thought to be simply a force that acted between objects, like how two magnets might attract each other. But general relativity showed that gravity is not a force in the traditional sense. Instead, it is the result of the warping or bending of space-time caused by mass and energy. In other words, massive objects bend space-time, and smaller objects move along these curves. The more massive the object, the more it bends space-time, which is why, for example, Earth orbits the Sun. The Sun's mass curves space-time, and Earth follows the curved path. This idea that space-time can bend and curve leads to a fascinating realization. There might not be a boundary to the universe in the way we usually think of it. The curvature of space-time doesn't have an edge in the traditional sense. Instead, space-time itself can extend infinitely, curving and stretching without needing a final end. The universe could be infinite with no physical boundary, simply because space-time itself is not a flat, rigid structure. It is fluid and dynamic, always stretching and evolving. One of the thinkers who explored this idea in a groundbreaking way was John Wheeler, an American physicist who made major contributions to our understanding of black holes and space-time. Wheeler took Einstein's ideas and expanded them, applying them to some of the universe's most mysterious phenomena, including black holes. One of his most famous contributions was the concept of black hole thermodynamics, which combines the principles of thermodynamics with the behavior of black holes. In Wheeler's view, black holes were not just objects that devoured matter. Instead, he saw them as fundamental pieces of space-time, providing deep insights into how the universe itself functions. Black holes, in this sense, were windows into the very nature of space and time. In fact, Wheeler proposed that the entire universe might be a giant black hole, a concept that is as mind-boggling as it is fascinating. In this model, the universe's structure could be thought of as a gigantic black hole, where all of space and time is contained within a vast singularity-like region. This idea forces us to reconsider the entire concept of edges in the universe. Rather than being a boundary, a black hole could be a portal into another part of the universe, or even another universe entirely, with space-time continuing beyond what we can observe. This brings us to a thought-provoking reflection by Carl Sagan, the famous astronomer and science communicator. Sagan often spoke about the idea that space itself might not have an edge, but could instead curve back on itself. In his view, the universe could be infinite and continuous, with no boundary separating it from what lies beyond. In this context, the curvature of space-time makes the universe seem infinite, without a definitive edge. The universe is vast, yes, but it is also self-contained, meaning that what we perceive as the end of the universe might simply be the limit of what we can observe, not the true end of space itself. What's particularly exciting about the idea of space-time curvature is that it opens the door to the possibility that space itself may be a higher dimensional construct, not bound by the 3 dimensions we're familiar with. This is where things start to get even more speculative. While we usually think of space as 3-dimensional, height, width, and depth, there are theories that suggest there could be more dimensions hidden from our perception. Some of these ideas are part of string theory, a framework that proposes the existence of additional dimensions beyond the 3 we can directly observe. In string theory, these extra dimensions are compacted, meaning they are curled up so tightly that they're invisible to us. But the very existence of these extra dimensions could explain some of the strange behaviors of space-time, including the curvature we observe in the presence of massive objects. These higher dimensional ideas, while still highly theoretical, suggest that space itself might not be as simple as we imagine. What if, instead of a flat 3-dimensional space, the entire universe exists within a higher dimensional space, where what we experience as gravity is simply a projection of forces operating in these unseen dimensions? This idea would not only change the way we think about the structure of the universe, but could also unlock deeper understandings of how space-time functions on both the largest and smallest scales. If we look at the universe through the lens of general relativity, we see a picture that is both vast and deeply interconnected. Space-time is not just a passive backdrop for the events that occur within it. It is an active, dynamic player in the universe, shaping the paths that objects take and influencing the very fabric of reality itself. The curvature of space-time is a constant feature of the universe, and it is this curvature that helps us understand phenomena as diverse as the motion of planets, the bending of light near massive objects, and the mysterious nature of black holes. In the end, the curvature of space-time shows us that the universe might not have a clear edge in the way we typically imagine it. Instead, space and time are intertwined in a vast flowing continuum that shapes everything within it. General relativity, combined with the ideas of thinkers like John Wheeler, Carl Sagan, and those exploring higher dimensional space, suggests that the universe is much more complex and fluid than we once thought. There may be no real boundary to space, only limits to our ability to perceive it, and the more we understand about how space-time curves and expands, the more we realize that the true nature of the universe may be far stranger and more wonderful than we can imagine. Imagine a universe that is not static, but rather endlessly cycling through phases of birth, death, and rebirth. This is the premise of conformal cyclic cosmology, or CCC, a bold theory proposed by the renowned physicist Roger Penrose. Penrose's model takes a radically different approach to understanding the life cycle of the universe. In his view, the universe does not simply have a beginning with a Big Bang, followed by an inevitable end. Instead, he suggests that the universe goes through a series of cycles, with each one evolving from the previous one in a continuous loop. In conformal cyclic cosmology, each cycle is referred to as an aeon. The universe we experience is just one of many, each beginning with a big bang and stretching out over billions of years, expanding and cooling before eventually collapsing into a state of infinite expansion. But here's the twist. When the universe reaches a state where everything is extremely spread out and cold, it doesn't simply fade away. Instead, according to Penrose, the end of one aeon seamlessly transforms into the beginning of the next. The smooth and empty universe, with all its energy spread thin, becomes the perfect environment for a new cycle to emerge, starting again with another big bang. This model is not just a theoretical curiosity, it challenges traditional views of the universe, particularly the idea that the universe had a single, distinct beginning and will ultimately meet a final, irreversible end. Instead, the CCC theory presents a timeless vision of the universe, one that transcends the concept of an absolute beginning and end. In this view, time itself becomes cyclical, and space is bound to stretch on infinitely in these repeating cycles. This model pushes the boundaries of cosmological thinking, suggesting that the universe's true nature is not defined by a single linear timeline, but by a continuous, evolving pattern that spans across infinite cycles. While Penrose's cyclical universe offers a fascinating perspective, another groundbreaking theory suggests that the universe is even more deeply interconnected than we may ever realize. Enter David Bohm and his theory of the implicate order. Bohm, a theoretical physicist, proposed that the universe is not merely a collection of isolated objects, but rather a unified whole in which everything is deeply interconnected. His idea of the implicate order presents the universe as an unfolding interwoven fabric, where what appears to be separate is actually just a manifestation of deeper underlying processes. In Bohm's model, the observable universe is just the explicate order, the surface level that we can perceive with our senses and scientific instruments. But beneath that lies the implicate order, a hidden, deeper dimension of reality that governs the flow of everything in the universe. According to Bohm, the entire cosmos, every galaxy, star, planet, and particle, is an expression of this deeper order. This is a profound idea because it suggests that the universe we see with our eyes is only a tiny fraction of what truly exists. Everything we observe is a reflection of something more fundamental and more expansive, woven into the very fabric of space-time itself. Bohm's ideas about the implicate order are not only fascinating but also deeply philosophical. They blur the line between physics and metaphysics, proposing that our reality is not as fragmented as it seems. Instead, everything is connected, part of a larger unseen structure. This theory invites us to consider the universe as a much more fluid, dynamic, and interconnected place, where space and time are not merely passive backdrops, but active, evolving components of a grand, unified whole. But let's expand even further into the dimensions of space itself. The universe might not only be a collection of connected events unfolding across time, it might also be made of more than the three familiar dimensions of space we experience. This is where string theory and M-theory come into play. These theories propose that space is far more complex than we usually imagine. According to string theory, the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings of energy. These strings vibrate in different ways, and their vibrations give rise to the particles and forces that make up everything we observe. But string theory doesn't just stop at the three dimensions of space we experience. It suggests that there are additional hidden dimensions, up to 10 or 11, depending on the version of the theory. These extra dimensions are compacted, meaning they are so small that they're beyond our direct perception. We live in a three-dimensional world, but string theory suggests that the true nature of space is far richer and more complicated than we can observe. The extra dimensions in string theory could help explain the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, which behave differently in these higher dimensions. M-theory, a broader framework that emerged from string theory, takes this idea even further, suggesting that all of the various string theories are simply different manifestations of one unified theory. According to M-theory, the universe could be made up of not just one, but multiple dimensions, with the potential to influence the way we think about the edges of space. In M-theory, the universe may not have a clear-cut boundary, but could instead be part of a higher dimensional space, where space-time itself behaves in ways we can't yet fully grasp. The implications of these higher dimensions are profound. If there are additional dimensions beyond the ones we experience, space as we know it may only be a projection of a much larger reality. The boundaries we perceive in space might be entirely artificial, the result of our limited perception of a reality that exists across multiple dimensions. This kind of thinking stretches the concept of edges and limits to new heights, suggesting that the universe might not have boundaries in the traditional sense. Instead, space could be an infinitely complex multi-dimensional structure where the very idea of an end is not relevant. And then there's the foundational work by Georges Lemaitre and Alexander Friedman in the early 20th century, which laid the groundwork for the idea of an infinite universe. Lemaitre, a Belgian physicist and priest, proposed what we now call the Big Bang theory. He suggested that the universe began from a singular point of infinite density, often referred to as a singularity, and has been expanding ever since. His work was based on the equations developed by Alexander Friedman, a Russian physicist who showed that the universe could be expanding, starting from a single point and continuing outward indefinitely. These ideas directly challenge the previous notion of a static universe and open the door to the understanding that space might not only be vast, but might also be infinite, continually expanding and stretching outward across time. Together, the contributions of Lemaitre and Friedman provided the theoretical foundation for understanding that the universe we observe is not just large, it's potentially infinite, expanding without a clear edge or boundary. This view, which is at the heart of modern cosmology, suggests that the universe may never truly end. Instead, it could continue to stretch, expand, and evolve indefinitely, without any clear edge or stopping point. All these models, Penrose's cyclical universe, Bohm's implicate order, string theory, and the contributions of Lemaitre and Friedman, push the boundaries of how we think about space and time. They challenge our most fundamental ideas about the universe, and invite us to imagine a cosmos that is far more intricate and mysterious than we've ever conceived. Whether the universe is infinite, cyclical, or even a higher dimensional projection, each of these theories shows that the universe is far more than we can ever see or touch. The boundaries we perceive may be just the surface of a much deeper and far-reaching reality. Imagine standing under a vast starlit sky, gazing up at the galaxies, stars and nebulae scattered across the cosmos. What you see is only a small fraction of the universe. Far beyond what's visible lies a hidden world, one that has eluded detection for decades, but holds a profound influence on the universe's structure and expansion. This unseen realm is made up of two mysterious forces, dark matter and dark energy. These enigmatic components shape the universe in ways we can't directly observe, yet their impact is undeniable. Dark matter is something strange. It's invisible to the naked eye and doesn't emit or interact with electromagnetic radiation, meaning it doesn't give off light or heat, and yet scientists are certain it exists because of its gravitational effects on visible matter, like galaxies. In fact, without dark matter, galaxies wouldn't behave the way they do. If we look at the rotation of galaxies, we see that the outer stars are moving much faster than they should be if only visible matter, like stars and gas, were at play. There's not enough mass in the visible parts of the galaxy to explain this speed, so something invisible must be exerting gravitational influence, holding these galaxies together. This invisible substance has been given the name dark matter because it doesn't interact with light, making it completely undetectable by traditional telescopes. But just because we can't see it doesn't mean it's not there. Dark matter makes up about 25% of the universe's total mass energy content. That's a huge amount, far more than the matter we can observe. But what is dark matter exactly? The most widely accepted idea is that it's made up of particles that don't interact with light or any other electromagnetic force, but still exert gravitational effects. We're still not sure what these particles are, but theories suggest they could be weakly interacting massive particles, or WIMPs. Now here's where things get even more intriguing. What if dark matter is not just a substance that exists within our universe, but a shadow universe, a parallel realm that exists beyond the space we can observe? Some theories suggest that dark matter could be a window into a hidden part of the universe, existing alongside the familiar world we know, but just out of our reach. This shadow universe would be made of particles that don't interact with light, meaning we wouldn't be able to detect them directly. They could be influencing the universe in ways we can't fully perceive, like shaping the gravitational fields of galaxies and clusters. This idea is supported by the work of physicists like Nima Arkani-Hamed. Arkani-Hamed has suggested that dark matter could be a clue pointing to a much larger and more complex structure of reality. According to his theories, the universe may not be confined to the 3 dimensions of space that we experience. Instead, there could be hidden dimensions, extra-spatial dimensions beyond the ones we perceive. These extra dimensions could be the key to understanding dark matter. What if the particles making up dark matter are actually from these higher dimensions, interacting with our world in ways we don't fully understand? This notion comes from the broader framework of string theory, which proposes that the universe consists of not just the familiar 3 dimensions of space and 1 of time, but additional dimensions that are too small for us to detect directly. These hidden dimensions might be where dark matter exists, and studying it could give us a glimpse into a universe far larger and more intricate than we ever imagined. But dark matter is only half of the cosmic mystery. There's another force at work in the universe, one that affects its expansion. This force is dark energy. Dark energy is thought to make up about 70% of the universe's total energy content, yet we know very little about it. What we do know is that dark energy is responsible for the accelerated expansion of the universe. In the early 20th century, it was thought that gravity would slowly pull everything back together, eventually causing the universe to slow its expansion and collapse in on itself. But in the late 1990s, observations of distant supernovae showed that the universe wasn't slowing down, it was speeding up. This unexpected discovery led to the realization that something must be driving this accelerated expansion, that something is dark energy. Dark energy is a mysterious force that seems to have a repulsive effect on the fabric of space-time itself, pushing galaxies farther apart at an accelerating rate. It acts in opposition to gravity, which would normally pull objects together. The exact nature of dark energy remains one of the greatest unsolved mysteries in physics. Some theorists, including Sean Carroll, have suggested that dark energy could be linked to the energy of the vacuum itself, an idea that comes from quantum field theory. According to this theory, the vacuum of space is not empty, it's filled with fluctuating energy, and dark energy could be the manifestation of this vacuum energy, which pushes the universe apart. The influence of dark energy is profound because it could determine the ultimate fate of the universe. If dark energy continues to drive the universe's expansion, it might eventually lead to what scientists call the Big Freeze. In this scenario, the universe would continue to expand at an accelerating rate, causing galaxies to move farther and farther apart. Stars would burn out and galaxies would drift into isolation. Eventually, the universe would grow cold, dark, and empty. It's a fascinating and sobering vision of the future, where the cosmos reaches a state of maximum entropy and no new events take place. However, the ultimate fate of the universe might not be so simple. Dark energy could also have the potential to lead to a very different outcome. In some theories, if the amount of dark energy increases, it could eventually cause the universe to expand so quickly that it rips itself apart. This scenario, known as the Big Rip, would see galaxies, stars, and even atoms torn apart by the accelerating expansion. The idea of a Big Rip challenges our usual understanding of the universe's ultimate fate, suggesting that dark energy could bring about a violent and dramatic end. So, what does all of this mean for our understanding of the universe? Dark matter and dark energy are not just mysterious forces that fill the space between stars, they shape the universe itself, influencing its structure, its expansion, and potentially its ultimate fate. They point to the possibility of unseen forces, hidden dimensions, and deeper layers of reality that we've yet to fully explore. The more we study dark matter and dark energy, the more we realize how much we still have to learn about the universe, and how much stranger and more complex it might be than we ever imagined. Together, these two mysterious forces suggest that the universe is far more than we can directly observe. There may be vast regions beyond our detection, hidden realms where dark matter reigns, or even where dark energy drives the very fabric of space. These forces, along with the theories of extra dimensions and hidden realms, push the boundaries of our knowledge and hint at a reality that is far richer and more intricate than the universe we see with our eyes. And as we continue to study dark matter and dark energy, we might uncover even more surprises. each one bringing us closer to understanding the true nature of the cosmos. The idea of the multiverse is one that stretches the imagination and challenges everything we thought we knew about the universe. The concept is simple yet profound. What if the universe we observe is just one of many, each with its own set of physical laws, constants, and structures? This notion goes beyond the idea of infinite space, suggesting that there could be multiple universes, each existing alongside one another, possibly with their own unique realities. This concept of the multiverse has emerged from some of the deepest and most intriguing questions in modern physics, inviting us to rethink the very nature of existence and space itself. One of the first theories to introduce the idea of parallel universes came from Hugh Everett, a physicist in the 1950s. Everett proposed the many worlds interpretation of quantum mechanics, which fundamentally changes how we view the quantum realm. Quantum mechanics is the branch of physics that deals with the behavior of particles at the smallest scales, atoms, electrons, photons, and it's famously strange. Particles can be in multiple states at once, a phenomenon known as superposition. For example, an electron can be in more than one place at the same time until it's observed, at which point it chooses one position. Everett's groundbreaking proposal was that instead of collapsing into one state upon observation, as traditional quantum mechanics suggests, all possible outcomes actually occur. Each possibility exists in its own parallel universe. This idea meant that every time a quantum decision is made, every time a choice is presented in the quantum world, a new universe is created, with each universe representing one of the possible outcomes. So, according to the many worlds interpretation, there's no need to collapse probabilities into a single outcome. Instead, the universe splits, and each version of reality plays out in its own distinct world. This interpretation opens up the idea of an infinite number of parallel universes, each with its own version of events, each universe slightly different from the others based on the decisions made at the quantum level. Imagine, for example, that you make a decision, one that seems trivial, like what to have for breakfast. According to many worlds, at that moment the universe splits, creating one universe where you choose eggs and another where you opt for cereal. On a grander scale, this idea suggests that every possibility, from the birth of stars to the paths of entire galaxies, could be playing out in multiple versions of reality, each universe unfolding with its own history and outcomes. Expanding on this, David Deutsch, a leading figure in quantum computation, has taken Everett's ideas further, suggesting that quantum mechanics might support not only parallel universes, but also the possibility of multiple universes that coexist with different physical laws. Deutsch's work on quantum computing presents the idea that quantum computers could harness the power of these multiple universes, using the parallel realities to compute in ways that classical computers cannot. In his view, these multiple universes aren't just abstract possibilities, they could be physically real and interwoven into the fabric of existence. This suggests that our universe, with all its laws and constants, is just one of many, each existing in a vast, unobservable multiverse. Deutsch's perspective adds another layer of complexity to the multiverse theory. It isn't just that other universes exist, they could potentially be connected in ways that we don't yet understand. The idea of quantum computing tapping into the potential of multiple universes invites us to think about space and time in ways we have never considered before. It suggests that our reality is part of a much larger structure, a multiverse of possibilities where the laws of physics could vary from one universe to the next. Then, there's the string theory multiverse, a model that extends the concept of the multiverse even further. Brian Greene, one of the leading proponents of string theory, suggests that our universe might not be the only one in existence. In fact, it might be just one of countless universes within a much larger multiverse. String theory, which proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings, suggests that there are extra dimensions of space beyond the three we are familiar with. These extra dimensions are curled up, compacted so tightly that we cannot perceive them directly. But if these dimensions exist, they could lead to the formation of multiple universes, each with its own set of laws and properties. In the string theory multiverse model, each universe could have a different configuration of these extra dimensions, which would give rise to different physical laws. Some universes might have different constants for gravity, or even different numbers of spatial dimensions. This means that the very fabric of space-time could be shaped in vastly different ways in different universes, each with its own unique reality. The string theory multiverse also proposes that the constants of nature, like the strength of gravity or the charge of an electron, could vary across these universes, leading to a diverse set of cosmic environments. The implications of the multiverse are far-reaching. If these other universes do exist, it could change the way we think about the boundaries of space and time. The universe we observe might only be a small part of a much larger, interconnected whole. What we experience as our universe might be one of many, existing in parallel with others that have different physical laws, histories, and outcomes. And perhaps, in some of these other universes, the laws of physics are not conducive to life as we know it, while in others, the possibilities for existence are even more diverse than we can imagine. The multiverse theory also raises profound questions about the nature of existence itself. If there are infinite universes, each with its own version of reality, what does that mean for the concept of uniqueness? Are we truly special in this universe, or are we just one version of a multitude of possibilities? Could our actions have infinite consequences, with each decision creating a new universe where that possibility unfolds? These questions challenge our most basic ideas about space, time, and reality, pushing the boundaries of scientific thought and inspiring new ways of looking at the universe and our place within it. Yet, for all its intrigue, the idea of the multiverse remains speculative. While the theories of many worlds, quantum computation, and string theory offer compelling visions of a multiverse, they are still just that. Visions. There's no direct evidence for the existence of parallel universes, and the models themselves face significant challenges in terms of testing and verification. The idea of a multiverse may be a consequence of theoretical frameworks that are not yet fully understood or tested, leaving us with more questions than answers. Still, the multiverse theory pushes the boundaries of what we consider possible in the universe. It forces us to rethink the very nature of space and time, suggesting that our universe might not be an isolated entity, but part of a much larger and more complex reality. Whether or not the multiverse exists, the exploration of these ideas has already had a profound impact on science, leading to new ways of thinking about the universe, its origins, and its ultimate fate. As we look to the future, the pursuit of understanding the multiverse will likely continue to challenge and inspire scientists, philosophers, and curious minds alike. While we may never directly observe these other universes, the theories that support their existence help us expand our horizons, taking us to the very edges of what is possible and pushing the boundaries of space itself. And in that quest, we find the true excitement of discovery, the constant expansion of knowledge, the opening of new frontiers, and the endless possibilities that lie just beyond the observable universe. The question of whether the universe is infinite or finite has been one of the most profound and debated topics in cosmology. It touches on our understanding of the universe's origins, its current structure, and ultimately its fate. For centuries, scientists, philosophers, and thinkers have grappled with this question, and even today, we are still not certain of the answer. The debate continues to evolve, driven by new discoveries and increasingly sophisticated theories. One of the key issues in this debate is the idea of whether the universe has a clear boundary or edge. Traditional models, based on an infinite static universe, suggest that space extends endlessly, without any beginning or end. This is a tempting thought, an infinite universe where space stretches out in all directions forever. In this view, the universe has no true limits, and the stars and galaxies we see are just tiny specks in a vast, unending sea of space. But as we began to understand the true nature of the cosmos, this view became more complicated. In the early 20th century, the discovery that the universe is expanding forever changed how we think about the universe's size. Edwin Hubble showed, through his observations of distant galaxies, that they are all moving away from us, implying that the space between them is stretching. This discovery gave rise to the Big Bang theory, which suggests that the universe began as an incredibly hot and dense point around 13.8 billion years ago and has been expanding ever since. This expansion introduced a new question. If space is expanding, what does that mean for the edge of the universe? If space itself is stretching, then perhaps the universe doesn't have a hard boundary. Instead, it may be infinite in some sense, continuously expanding outward in all directions. This would mean that the observable universe, the portion we can see and measure, is only a fraction of a much larger, possibly infinite reality. This idea of an infinite universe is deeply linked to the concept of cosmic inflation, a theory proposed by Alan Guth in the 1980s, which suggests that in the first moments after the Big Bang, the universe expanded at an incredibly fast rate. This inflationary period would have stretched the universe so rapidly that it effectively erased any clear edge, creating a universe that is vast beyond measure, with no definitive boundaries. However, this notion of an infinite universe does not come without its challenges. Some scientists have proposed alternative models that challenge the idea of an infinite cosmos. One such model is based on the idea of a finite universe. The idea here is that while the universe is expanding, it might still be finite, with a specific size and shape. In this view, the universe might be curved or closed, like the surface of a sphere, meaning that if you travelled far enough in one direction, you would eventually end up where you started, much like walking in a straight line on the Earth's surface. This kind of universe, while finite, would still have no edge in the traditional sense, just as the surface of the Earth is finite but doesn't have an actual boundary. Instead, it would be a finite but unbounded space, where the curvature of space-time causes the universe to loop back on itself. The infinite versus finite debate is further complicated by the work of David Bohm, a theoretical physicist who proposed a deeply interconnected view of the universe. Bohm's idea, known as the implicate order, suggests that the universe is not just a collection of separate objects, but a single, unified whole. In his view, everything is interconnected, and space itself is not just an empty backdrop for events, but an active, dynamic field that connects all things. Bohm's theory challenges the idea of a clear-cut edge to the universe, suggesting that the very notion of boundaries is a product of our limited understanding. Instead of seeing the universe as a collection of isolated galaxies, Bohm proposed that the universe is a seamless, interconnected whole, where everything is woven together by an underlying order that we can't directly perceive. Max Tegmark, a physicist at the Massachusetts Institute of Technology, offers another perspective with his mathematical universe hypothesis. Tegmark's theory suggests that the universe is not simply made up of physical particles and forces, but is actually a mathematical structure. In his view, space and time are just mathematical abstractions, and the universe itself is a mathematical object. This theory challenges the traditional idea of a physical universe with boundaries, suggesting instead that the universe is a mathematical construct that could be infinite or finite, depending on how the mathematics are applied. For Tegmark, the universe is not limited by physical constraints, but by the mathematical principles that govern it. This approach blurs the line between the finite and the infinite, as the boundaries of space and time could simply be mathematical features of a deeper underlying structure. Alongside these theoretical developments, Kurt Gödel, one of the greatest mathematicians of the 20th century, made an important contribution to the debate about the finite versus infinite universe. Gödel's work on rotating universes provided a fascinating twist to our understanding of space-time. In his model, the universe could be finite yet still have no boundaries. Gödel's rotating universe suggests that time itself could loop back on itself, creating a situation where the universe is finite, but doesn't have an edge in the way we usually think of one. In this model, you could travel through space and time, and if you kept going in a straight line, you would eventually end up back where you started, not because of any physical boundary, but because of the way space-time curves and twists in on itself. Gödel's work also implies that the universe might not be as simple as a series of expanding galaxies. Instead, the fabric of space-time could be dynamic, twisting and turning in ways that we don't fully understand. This adds another layer of complexity to the debate over whether the universe is infinite or finite. If space-time can curve and loop in on itself, it suggests that the very concept of a boundary may not apply to the universe in the way we usually think about it. This brings us to the concept of cosmic inflation, which has become a cornerstone of modern cosmology. Cosmic inflation is the idea that, in the very early moments after the Big Bang, the universe expanded at an exponential rate. This rapid expansion would have caused the universe to grow from a tiny dense point to the vast stretched-out cosmos we observe today, all in a fraction of a second. The implications of cosmic inflation are profound because they challenge the notion of a clear-cut edge to the universe. Instead of the universe expanding into some pre-existing space, inflation suggests that space itself is expanding, creating a universe that may be infinite in its extent. The expansion of space during inflation was so rapid that it could have smoothed out any irregularities or boundaries, making the universe appear homogeneous and boundless. The debate between infinite and finite universes ultimately comes down to how we understand space itself. Is space something that stretches out infinitely without any true edge? Or is it a finite closed system where the universe loops back on itself, like a balloon expanding in all directions? The work of scientists like Bohm, Tegmark and Gödel has pushed us to reconsider our most fundamental assumptions about space and time. Their theories suggest that the universe may be far more complex than we ever imagined, perhaps infinite, perhaps finite, but always shaped by forces and laws that we're still learning to understand. As our understanding of the universe continues to evolve, the question of whether the universe is infinite or finite remains an open one. New discoveries in cosmology, driven by tools like the Hubble Space Telescope and the James Webb Space Telescope, may eventually provide more clues. But for now, the debate continues, challenging us to think more deeply about the nature of space and time and whether the universe, in all its vastness, has a clear boundary, or if it stretches on forever, beyond our ability to perceive. When we think of the universe, we often picture space and time as two separate entities. Space is the vast three-dimensional expanse where all things exist, while time is the unidirectional flow that moves from past to present to future. But in the early 20th century, Albert Einstein's theory of general relativity upended this familiar understanding. It showed us that space and time are not independent, but are intimately connected in a unified entity known as space-time. In Einstein's view, space and time are not separate and independent. Instead, they are woven together into a four-dimensional fabric. This fabric is dynamic, and its shape can be influenced by mass and energy. A massive object like a planet or a star warps the fabric of space-time around it, creating what we perceive as gravity. The more massive an object, the greater its warping effect. This bending of space-time changes the way objects move, pulling them toward each other. In a sense, objects in space are following the curves in space-time, just as a marble might follow the curves of a warped rubber sheet. This interconnected nature of space and time gives us a radically different way of thinking about the universe. It suggests that space is not a passive, empty backdrop for events to unfold. Instead, space-time is an active, dynamic component of the universe, constantly changing in response to the objects and energy within it. This understanding has deep implications, especially when we start to think about time itself. One of the most fascinating consequences of general relativity is the concept of closed time-like curves, CTCs, first proposed by the mathematician Kurt Gödel in 1949. A closed time-like curve is essentially a loop in the fabric of space-time, where time itself behaves in a way that allows you to travel back to your own past. Imagine that you could take a journey through space, moving through a loop in space-time, and eventually find yourself back at the point in time where you started. This sounds like something out of science fiction, but according to Gödel's equations, it is theoretically possible within the framework of general relativity. Gödel's rotating universe model showed that, under certain conditions, space-time could be curved in such a way that closed time-like curves could form. These curves would allow for time travel to the past, creating a paradox where events could influence their own outcomes. In a way, this suggests that the flow of time isn't as fixed and linear as we tend to think. Time could, theoretically, loop back on itself, creating an endless cycle. This idea challenges our usual understanding of time as a one-way progression from past to future, and opens up strange and thought-provoking possibilities about the nature of time itself. But what if time doesn't work the way we think it does at all? What if time, as we understand it, is just an illusion? This is the premise of Julian Barber's timeless universe theory. Barber, a British physicist, proposed that time might not be a fundamental aspect of reality. Instead, he argued that time could be an emergent property, something that arises from the relationships between objects in the universe. According to Barber, the flow of time we experience may not be a fundamental feature of the universe, but a byproduct of the changing configurations of matter and energy. In his view, the universe exists in a series of now moments, each one frozen in time, and the illusion of time comes from the transition between these moments. In Barber's model, The universe doesn't progress in a linear fashion, with one moment following another. Instead, it exists as a series of static configurations, with the flow of time being a construct created by the changing relationships between these configurations. This theory challenges our most basic assumptions about time, suggesting that it's not a universal objective reality, but something that emerges from the physical structure of the universe. If Barber's theory is correct, it would mean that our experience of time is merely a mental construct, an illusion created by our perception of change. The concept of time as an illusion or an emergent property has profound implications for how we think about the beginning and the end of the universe. If time doesn't have a fundamental existence, then the idea of the beginning and end of time might not be meaningful. The Big Bang, traditionally thought of as the beginning of time itself, might not be a true starting point. Instead, time could be a feature of the universe that emerges as the universe evolves. Similarly, the end of the universe, whether it's the heat death, the Big Crunch, or some other fate, might not signify the end of time itself, but rather the end of the processes that create our perception of time. This view also reshapes our understanding of the boundaries of space. If time is not fundamental, then perhaps the universe itself doesn't have an ultimate boundary or end. The universe could simply exist in a timeless state, where all configurations of matter and energy coexist in a kind of static equilibrium, with no ultimate beginning or end. This idea of a timeless universe echoes some of the concepts explored by Roger Penrose in his conformal cyclic cosmology theory, where the universe undergoes infinite cycles of birth and death, with no clear boundary separating one cycle from another. If time is an illusion, then the universe itself might be infinite, stretching across an eternal cycle with no definitive beginning or end. The interplay between time and space raises some fundamental questions about the nature of reality itself. If time is not what we think it is, and if the universe doesn't have a clear boundary, what does this mean for our understanding of existence? Are we merely experiencing a fleeting moment in an eternal, timeless cosmos? Or is our perception of time just one of many possible realities, each emerging from the underlying structure of space and matter? These questions are not just philosophical. They have real implications for how we understand the universe and our place in it. If time is not a fundamental feature of the universe, then our understanding of the beginning of the universe, its future, and even the structure of space itself must be reconsidered. The way we perceive the flow of time may not be an accurate reflection of the true nature of the cosmos. Instead, the universe might be an eternal dynamic system, constantly evolving, with time and space as emergent properties of that system. The interconnected nature of time and space, as described by general relativity, and the possibility that time itself might be an illusion, challenges us to rethink our most basic concepts about reality. Whether we're considering the loops of closed time-like curves, the cyclical nature of the universe, or the idea of time as an emergent property, it's clear that our understanding of time and space is still in its infancy. As we continue to explore these ideas, we may uncover new insights that push the boundaries of what we think we know about the cosmos. Time, it seems, may not be as linear and fixed as we once believed. Instead, it could be a much more fluid and malleable concept, shaping the universe in ways we're only just beginning to understand. Quantum mechanics, a cornerstone of modern physics, is fundamentally different from the classical physics we use to describe the everyday world. It deals with the behavior of matter and energy at the smallest scales, those of atoms and subatomic particles, where the usual rules of space and time seem to break down. At these tiny scales, particles don't behave like solid objects with predictable paths. Instead, they exist in a state of probability, where they can be in multiple places at once or take multiple forms until observed. This uncertainty is encapsulated in what is known as Heisenberg's uncertainty principle, which states that we cannot simultaneously know the exact position and momentum of a particle. One of the most striking features of quantum mechanics is the wave-particle duality, which means that particles such as electrons can act both like particles and like waves, depending on how they are observed. This behavior seems to defy our usual understanding of space and time. In the quantum world, things are not solid and predictable. They are probabilistic and inherently uncertain. And yet, despite its weirdness, quantum mechanics is one of the most successful theories in physics, accurately predicting the behavior of particles and leading to the development of technologies like semiconductors and lasers. But while quantum mechanics works incredibly well at small scales, it hasn't yet been reconciled with the theory of general relativity, which describes the force of gravity on large scales. This gap between quantum mechanics and general relativity is one of the biggest challenges in modern physics. How does gravity, which is described by the smooth, continuous fabric of spacetime in general relativity, fit into the probabilistic, discrete world of quantum mechanics? To answer this question, scientists have proposed a range of new theories, and some of the most intriguing ideas suggest that gravity, and by extension space itself, might not be what we think it is. One such theory comes from Eric Verlinde, a physicist who proposed that gravity might not be a fundamental force of nature, but rather an emergent property. In other words, gravity could arise from the interactions of underlying microscopic particles, rather than being a basic force that acts directly between objects. Verlinde's idea stems from the notion that gravity, like other forces, may emerge from the collective behavior of more fundamental elements, much in the same way that temperature emerges from the motion of atoms. If gravity is an emergent property, this could drastically reshape our understanding of space's boundaries. It could mean that the fabric of space itself is not a static, fixed entity, but something that arises from deeper layers of reality, perhaps even from quantum processes that we don't yet fully understand. Verlinde's theory challenges the traditional view of spacetime as a smooth, continuous fabric. If space and gravity are emergent, this suggests that the boundaries of space are not fixed or inherent, but could change depending on the underlying quantum processes. The concept of emergent gravity also points to the possibility that space, as we understand it, could be an illusion, a phenomenon that arises from deeper quantum mechanical interactions. This radical idea raises questions about the nature of space itself. If space can emerge from more fundamental principles, what does that mean for the limits of space, both observable and beyond? Another physicist exploring the boundaries of space and the nature of gravity is Lee Smolin, whose work on quantum gravity challenges our understanding of space-time. Smolin's theories, particularly those related to loop quantum gravity, suggest that space itself is not a smooth, continuous fabric, but is instead composed of discrete quantized chunks. In his view, the fabric of space-time is made up of tiny, indivisible units, like atoms, that interact with each other in complex ways. These tiny units of space could be what give rise to the smooth continuum of space-time that we observe at macroscopic scales. Loop quantum gravity suggests that the very geometry of space-time is granular at the smaller scales, meaning that, on the smallest levels, space is not continuous, but made up of discrete, indivisible atoms of space. This granular view of space challenges our traditional understanding of the universe's boundaries. If space is composed of discrete units, this raises the possibility that the edges of the universe are not well defined in the way we might imagine. Instead, the universe's boundaries could be fuzzy, affected by the underlying quantum structure of space itself. This idea suggests that the universe may not be a smooth, infinite expanse, but rather a collection of discrete units of space that can interact with each other in ways we're only beginning to understand. Perhaps one of the most mind-bending ideas to come out of modern physics is the holographic principle, which suggests that the universe we perceive as three-dimensional might actually be a projection from a two-dimensional surface. This idea comes from work by Gerard 't Hooft and Leonard Susskind in the 1990s, who proposed that all of the information contained in the three-dimensional universe we experience could be encoded on a two-dimensional surface, much like a hologram. In this view, our entire universe, including space, time, and everything within it, could be a kind of holographic projection, where the real, underlying reality exists on a distant two-dimensional surface. The holographic principle arose from research into black holes and their strange properties. When physicists studied the information paradox associated with black holes, they realized that the amount of information that could be contained within a black hole was proportional not to its volume, but to its surface area. This observation led to the idea that the true nature of space-time might be fundamentally two-dimensional, and that the three-dimensional universe we experience is an illusion created by the way information is projected from this surface. If the universe is a projection, this could fundamentally change our understanding of space's boundaries. The boundaries of space, in this case, wouldn't be physical edges, but could be related to the way information is encoded and projected onto the two-dimensional surface. This idea suggests that our perceptions of space, time, and reality could be limited by the information available to us, and that the true structure of the universe might be hidden from our direct observation. The implications of these ideas are profound. They challenge our most basic assumptions about the nature of reality, space, and time. If gravity is an emergent property, if space-time is granular, or if the universe is a hologram, then the concept of edges becomes much more complex and elusive. Space might not be an infinite continuous fabric, but something far stranger, something that emerges from deeper quantum processes or that exists in a higher dimensional space. These theories push the boundaries of our understanding and suggest that space, as we perceive it, could be an illusion, shaped by forces and principles we don't yet fully understand. As we continue to explore these ideas, we may uncover a deeper understanding of the universe and its boundaries. Whether space is continuous or discrete, emergent or fundamental, the theories of quantum mechanics and gravity offer us new ways of thinking about the cosmos. They remind us that the universe is far more complex than we can immediately perceive, and that the boundaries of space may not be fixed. They may be fluid, changing, and influenced by forces that go beyond our current understanding, and in that mystery there's an infinite potential for discovery. When we gaze up at the night sky, we see the observable universe, a vast expanse of stars, galaxies, and cosmic structures stretching out in all directions. But what lies beyond that? What exists beyond the limits of what we can observe, beyond the farthest reaches of light that have travelled across the vast distances of space to reach us? This is a question that has intrigued scientists for centuries, and while we may never be able to directly observe what's beyond the observable universe, theoretical models offer intriguing possibilities. One model that attempts to answer this question is the spherical universe model, proposed by Jean-Pierre Luminet. Luminet's idea suggests that the universe is finite but unbounded, much like the surface of a sphere. In this model, space itself is curved in such a way that there is no true edge to the universe, even though the universe itself is finite. This concept is similar to how the surface of the Earth is finite but has no edges or boundaries. If you were to travel in a straight line on Earth, you would eventually return to your starting point, as the surface is curved. Similarly, in a spherical universe, if you travel far enough in one direction, you would eventually end up back where you started, but there would be no edge or end to encounter along the way. This model helps resolve some of the questions surrounding the limits of space. If the universe is spherical in nature, then the apparent edge of the observable universe is simply a limit to what we can see, based on the speed of light and the age of the universe. Beyond that, the universe would continue, but we would be unable to observe it because light from those regions has not had enough time to reach us. The spherical model suggests that the universe is finite in size, but doesn't have a boundary or an edge in the way we typically think about it. Instead, it's like a closed surface, wrapping back on itself, with no true beginning or end. This idea challenges the notion of a boundary in the traditional sense, offering a more dynamic, continuous view of space. But what if the universe itself isn't just a vast unbounded sphere? What if our universe is part of something even larger, a multiverse? The concept of the multiverse suggests that our universe is just one of many, each with its own set of physical laws and properties. The idea of a multiverse challenges the notion of a single, unique universe, and opens up the possibility that there are countless other universes out there, potentially with different versions of physics, different constants, and even entirely different types of life. One of the key ideas behind the multiverse is that the universe we observe might be just one bubble in a vast cosmic foam. This foam could contain many different universes, each separated by vast distances or existing in entirely different dimensions. These universes could have different laws of physics, different values for fundamental constants, and even different forms of matter and energy. In some versions of the multiverse theory, these universes might interact with each other, while in others, they could exist independently, with no direct connection between them. The concept of the multiverse suggests that our universe, with all its complexity and structure, might be just one of an infinite number of universes, each following its own set of rules and evolving in its own way. One way the multiverse is conceptualized is through the framework of cosmic inflation, a theory that suggests the early universe underwent an extremely rapid expansion. This inflationary period would have stretched space-time so quickly that it created multiple bubbles of space, each one evolving into a separate universe. These bubbles could have different properties depending on how inflation unfolded in each region, giving rise to a variety of universes with different physical laws. This idea is known as eternal inflation, and it suggests that the multiverse is not just a static collection of universes, but an ever-expanding and ever-evolving structure. The multiverse concept expands our understanding of space and time, proposing that what we perceive as the universe might be just one part of a much larger, more complex reality. Another fascinating perspective on the nature of the universe comes from David Deutsch, a physicist who has proposed a radical idea about the nature of reality. Deutsch suggests that the universe itself could be a simulation, or, more specifically, a mathematical construct. In his view, the universe isn't just a physical reality, it's a vast mathematical entity that exists in a deeper, more abstract space. According to Deutsch, the laws of physics, the structure of space-time, and the very nature of reality might be the result of mathematical relationships rather than physical interactions between matter and energy. This idea is rooted in the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event occurs in its own separate universe. Deutsch extends this idea to the entire universe, proposing that the entire cosmos is a kind of computation, a mathematical object that exists in a higher dimensional space. In this framework, the universe we observe is just one realization of an infinite number of possible mathematical structures, each with its own set of physical laws. The universe, then, might not be a physical entity at all but a mathematical construct, unfolding according to the rules of a deeper underlying reality. This view of the universe as a mathematical construct challenges our traditional understanding of space and time. It suggests that space itself might not be an intrinsic part of reality, but rather an emergent property that arises from the deeper mathematical structure of the universe. In this view, the edges of the universe are not physical boundaries, but the limits of our understanding and perception. The universe may be a projection of a much larger, more complex reality, and the true nature of space might lie beyond our ability to observe it directly. As we consider these different models, Luminet's spherical universe, the multiverse, and Deutsch's mathematical construct, we are confronted with the realization that the universe might be far stranger and more complex than we can imagine. Each of these models offers a different perspective on the boundaries of space, suggesting that the universe could be finite but unbounded, infinite, or even part of a much larger, multiversal structure. Theoretical models like these challenge our most basic assumptions about space, time, and reality, inviting us to think beyond the limits of what we can observe and explore new possibilities for what might lie beyond the observable universe. These ideas raise profound questions about the nature of existence itself. If the universe is part of a larger multiverse, what does that mean for our understanding of life and consciousness? Are we just one small part of a vast infinite reality, or do we exist in a universe with unique properties that make it special? And if the universe is a mathematical construct, what does that say about the relationship between mathematics, reality, and the laws of physics? These questions don't have easy answers, but they push us to think more deeply about the universe and our place within it. Ultimately, these theoretical models remind us that the universe is far more than what we can see and measure. It is a vast, mysterious entity, one that might be much larger and more complex than we ever imagined. Whether it is a spherical universe with no edge, a multiverse of infinite possibilities, or a mathematical construct unfolding in higher dimensional space, the true nature of the universe lies beyond the limits of our current understanding. But that doesn't mean we won't keep searching, because the answers to these questions could hold the key to unlocking the deepest mysteries of existence itself. The end of the universe. It's a concept that sparks both wonder and dread. How will the universe come to an end? Will it be a quiet fade into nothingness, or a dramatic event that causes everything we know to collapse in on itself? These questions have fascinated scientists and philosophers for centuries, and while we may not have a definitive answer, we do have several intriguing theories that try to predict the universe's ultimate fate. These theories also provide new insights into the nature of space itself, particularly the boundaries of space, whether they exist at all or if space, like the universe, has no true end. One of the most widely discussed theories about the end of the universe is the Big Freeze. This scenario is based on the observation that the universe is expanding at an accelerating rate. As distant galaxies move away from us, they're moving faster and faster, driven by the mysterious force known as dark energy. If this acceleration continues indefinitely, the universe will keep expanding and all of its galaxies will eventually move beyond the reach of one another. Stars will burn out and galaxies will drift further apart. Eventually, the universe will become a dark, cold place, where the energy required to sustain life, or even star formation, will be gone. In this scenario, the end of the universe is not a dramatic explosion or collapse, but a slow, inevitable fading into darkness and emptiness. The Big Freeze implies that space itself will continue to stretch out indefinitely. There won't be any edge to space. It will simply keep expanding, and the distances between objects will keep growing. The observable universe, defined by the farthest light we can see, will keep shrinking as objects move farther away, eventually becoming invisible to us. Even though the universe itself will keep expanding, there will be no clear end or boundary, just an ongoing, slow process of isolation. This raises interesting questions about the very nature of space. If the universe becomes increasingly empty, with all galaxies drifting apart, does space itself eventually become a void, devoid of matter, energy, or even observable structure? And if so, does this truly signify the end of space? Or is it simply the universe reaching a state where its boundaries are too far to comprehend? Another possible fate for the universe is the Big Crunch. This theory is based on the idea that the expansion of the universe could eventually slow down and reverse, causing everything to collapse back in on itself. If the gravitational pull of all the mass in the universe is strong enough, it could overcome the expansion driven by dark energy. In this scenario, the universe would begin contracting, with galaxies, stars, and planets drawn closer together. As the universe shrinks, temperatures would rise to extreme levels, and the fabric of space-time could stretch and bend under immense pressure. The Big Crunch could ultimately end with a singularity, a point of infinite density, similar to the one that marked the beginning of the universe. This theory would suggest that the universe has not only a beginning but also an end, a cyclic pattern where it collapses and then potentially starts anew. What does the Big Crunch imply for space? If the universe were to collapse in on itself, it would mark a dramatic end to the concept of space as we know it. The boundaries of space would collapse, and space-time itself would undergo extreme distortions, perhaps to the point where traditional concepts of space and time no longer apply. In this sense, the end of the universe could coincide with the end of space itself, as the collapse of the universe would essentially unravel the structure of space-time. In such a scenario, the boundaries of space, as we understand them, would cease to exist altogether. The third major theory about the end of the universe is the Big Rip. This is a more extreme possibility, where the universe's expansion accelerates so rapidly that eventually not just galaxies, but even atoms, stars, and planets would be torn apart. The force of dark energy would become so intense that it would overcome the gravitational forces binding objects together, causing them to disintegrate at the most fundamental level. In the Big Rip scenario, space itself would be stretched to its breaking point, ultimately ripping apart all structures in the universe, from the largest galaxies down to the very fabric of space-time itself. The Big Rip challenges our traditional understanding of space's boundaries in a dramatic way. Space would not only expand, but would do so with such violence that its very structure could be torn apart. In this sense, the boundaries of space would not be something distant or invisible, but something actively unstable, capable of collapsing and reforming as the universe reaches its ultimate end. This possibility suggests that space could have an edge, in the most literal sense, where its very fabric breaks down entirely under the influence of dark energy. While these three theories, the Big Freeze, Big Crunch, and Big Rip, offer different scenarios for the end of the universe, they all point to one profound conclusion. The end of the universe is likely tied to the end of time itself. If the universe reaches a point where it either slows down and contracts, or accelerates and tears apart, the flow of time as we experience it could cease. If space is continually expanding and stretching into a cold, empty future, time may no longer have any meaningful progression. Similarly, if the universe collapses in a Big Crunch, time would reverse, and the flow of time we know could collapse into a singularity. These theories suggest that the end of the universe, in whatever form it may take, is intimately connected with the ultimate fate of space and time. But what about the question of whether the end of space can ever be fully known? Can we truly understand the boundaries of space? Or are they simply beyond our comprehension? It's important to remember that the observable universe, the part we can study and measure, is only a fraction of the total universe. As the universe continues to expand, more and more of it moves beyond our observational reach. Even with the most advanced telescopes, we are limited by the speed of light and the expansion of space itself. This raises the intriguing possibility that there may be no true end to the universe at all, only a limit to our ability to observe it. The idea that the end of space might be unknowable introduces an element of mystery to the cosmos. No matter how much we learn, we may never fully comprehend the true nature of space's boundaries. Perhaps the universe is infinite, and we are simply unable to see the farthest reaches of it. Or perhaps space is finite, but it is expanding at a rate that will forever keep the farthest regions beyond our reach. The true end of space may always remain elusive, a mystery that no scientific instrument or theory can fully unravel. In the end, the question of the universe's fate and whether space has true boundaries remains one of the most intriguing and challenging topics in cosmology. Whether the universe ends in a big freeze, a big crunch, or a big rip, it will undoubtedly redefine our understanding of space and time. And in doing so, it may reveal that the boundaries of space are not fixed or final, but a part of a much larger, ever-evolving cosmic story. When we turn our attention to the question of space, it's not only the science that intrigues us. The idea of an infinite, boundless universe has deep philosophical implications that stretch back centuries. While cosmologists explore the mechanics of space, philosophers have grappled with the more abstract aspects. What does it mean for something to be infinite? Can we truly understand the nature of space? Or is it something forever beyond our comprehension? These questions force us to confront the limits of human knowledge and the very nature of reality itself. One of the earliest philosophers to address the nature of space was Immanuel Kant, whose ideas about the universe are still influential today. Kant, in his Critique of Pure Reason, proposed that the universe, in its entirety, is beyond human comprehension because of our inherent limitations. He distinguished between the world as we experience it and the world as it truly is. According to Kant, we can only know the phenomenon, the appearance of things, as they are perceived through our senses. The true nature of things, which Kant referred to as the noumenon, remains unknowable. In other words, while we can measure the space around us and observe the stars, galaxies, and cosmic structures, we cannot fully grasp the fundamental nature of space itself. It exists, Kant argued, but our minds are incapable of truly understanding it in its entirety. Kant's notion of noumenon suggests that there may always be limits to our understanding of space. Even if we are able to observe the universe through telescopes and scientific instruments, we are still constrained by our senses and the way our minds process information. For Kant, this means that space, and even time, are not absolute realities, but constructs of human perception. While space may exist independently of us, we can only ever experience a limited, filtered version of it. In this sense, the question of whether space is truly infinite or finite may be a question that remains outside the bounds of human understanding. The infinite universe could be an idea that exists only as a concept, something our minds cannot fully grasp. This philosophical inquiry into the nature of space and the limits of our understanding is not confined to the Enlightenment thinkers. In the 20th century, Martin Heidegger, a German philosopher, explored the existential significance of human existence in relation to the vastness of the universe. Heidegger's existential philosophy grapples with questions of being, time, and space, and it offers profound insights into how we experience the universe as finite beings in a seemingly infinite cosmos. For Heidegger, the human experience of space is deeply tied to our awareness of time. He argued that our understanding of the world is shaped by the way we move through it, by the passage of time, and by our eventual death. Our consciousness of being, he suggested, is always marked by an awareness of our own finitude. Space, in this sense, becomes a backdrop to the human experience of existence. But what happens when we face the vastness of space itself? The idea of an infinite universe, without boundary or limit, challenges our sense of self and our place within the cosmos. If the universe extends forever, then what does that mean for our small, finite existence? Heidegger's philosophy suggests that our struggle to comprehend an infinite, boundless universe reflects the deeper human anxiety about meaning and purpose. The endless expanse of space can make us feel insignificant, like tiny specks in an uncaring cosmos. And yet Heidegger also suggests that this very vastness may call us to reflect on our existence and our relationship with the world. The more we contemplate the boundlessness of space, the more we are forced to confront our own mortality, our place in the universe, and the fleeting nature of our lives. While philosophers like Kant and Heidegger grapple with the existential implications of infinity, scientists have also turned to the idea of the infinite to explore the structure of the universe. One particularly interesting concept that intersects science and philosophy is the anthropic principle. The anthropic principle suggests that the universe is not just a random collection of matter and energy, but that its very structure is fine-tuned to allow the existence of life, particularly human life. In other words, the conditions of the universe, the laws of physics, the values of fundamental constants, are such that they make the emergence of life possible. If the universe were just a vast, impersonal expanse, there would be no reason for it to be so well suited for life as we know it. The anthropic principle raises intriguing questions about the nature of space and the boundaries of the universe. If the universe is fine-tuned for life, does that suggest that the universe has an inherent purpose or direction? And if the universe is infinite, as some models suggest, could there be other regions of space where the conditions for life are different, or even entirely absent? The anthropic principle introduces a sense of intentionality into the universe, implying that the structure of space is not entirely random, but could be shaped by deeper, underlying principles that make life possible. This raises the possibility that the boundaries of the universe, or the limits of space, might not be as arbitrary as we once thought. They may be a necessary feature of a universe that allows for conscious beings like ourselves to exist. These philosophical perspectives force us to confront the limits of human understanding, whether we approach the question of space's boundaries from the standpoint of Kant's unknowable noumenon, Heidegger's existential reflections on the human condition, or the anthropic principle's suggestion that the universe is finely tuned for life. We are left with the realization that space, its true nature, its extent, and its purpose, may be far more mysterious than we can fully comprehend. The infinite universe may be both a scientific and a philosophical concept, one that challenges the very nature of reality and our place within it. In the end, the boundaries of space may never be fully known. Perhaps they are beyond human comprehension, just as the true nature of time or existence might be. But that doesn't mean we stop searching for answers. If anything, the pursuit of understanding space's boundaries, both scientifically and philosophically, is a reminder of the profound mystery of the universe. It's a journey that invites us to explore not just the cosmos, but our own place in it, how we, as conscious beings, experience the vastness of space and time, and how we come to terms with the infinite nature of reality. In recent years, the field of cosmology has taken remarkable strides in our understanding of the universe. Thanks to groundbreaking advancements in technology and observation, we now have tools that allow us to peer deeper into the cosmos than ever before. These new discoveries have the potential to reshape our understanding of space, time, and the very nature of the universe itself. One of the most exciting developments in modern cosmology is the launch of the James Webb Space Telescope, JWST. This powerful telescope, a collaboration between NASA, the European Space Agency (ESA), and the Canadian Space Agency, is set to revolutionize our view of the universe. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, the James Webb Space Telescope is designed to observe in the infrared spectrum. This capability allows it to peer through the dust clouds that obscure many of the objects we wish to study, providing a clearer view of the distant universe. The potential of the James Webb Space Telescope is truly remarkable. It is expected to provide detailed images of the earliest galaxies that formed after the Big Bang, possibly revealing the first stars and galaxies that existed just a few 100 million years after the universe's birth. JWST will also give us a better understanding of how galaxies, stars, and planetary systems evolve. Its observations could provide insights into the boundaries of the observable universe, revealing more about the regions we can't see, and perhaps offering clues about what lies beyond the limits of our current observational reach. In many ways, the James Webb Space Telescope is our next step in answering the age-old question of whether there are any true edges to space, or if the universe is infinite, stretching far beyond our comprehension. In addition to space telescopes like the JWST, another tool that has expanded our understanding of the universe is the Large Hadron Collider, LHC, located at CERN, the European Organisation for Nuclear Research. The LHC is the largest and most powerful particle accelerator in the world, and it has been instrumental in exploring the fundamental forces of nature. While it might seem far removed from the vastness of space, the LHC's discoveries have profound implications for our understanding of the universe's structure and its boundaries. One of the key achievements of the LHC was the discovery of the Higgs boson, the particle associated with the Higgs field, which gives other particles mass. This discovery confirmed a major part of the standard model of particle physics, but it also opened up new questions about the nature of the universe. For example, the LHC has allowed scientists to probe the behavior of dark matter and dark energy, two mysterious forces that shape the universe's expansion and structure. By studying the fundamental particles and forces in the universe, the LHC helps us understand how the fabric of space-time behaves on the smallest scales, which in turn informs our understanding of its larger structure and boundaries. But the LHC isn't just about understanding the small-scale structure of the universe. It also plays a role in examining the larger cosmic questions. One of the most intriguing possibilities is that the universe may contain extra dimensions beyond the familiar three of space and one of time. Some theories, like string theory and M-theory, suggest that there could be more than the four dimensions we experience, potentially leading to new insights into the boundaries of space. The LHC could, in theory, help us detect the presence of these extra dimensions, deepening our understanding of the universe's true structure. While the LHC delves into the small-scale forces that govern the universe, organisations like NASA and the European Space Agency, ESA, are focused on studying the universe's larger-scale structure and the forces that shape its expansion. One of their major ongoing efforts is to study the universe's early moments, particularly the period known as cosmic inflation. Cosmic inflation is a theory that suggests the universe expanded exponentially in the first moments after the Big Bang, growing faster than the speed of light for a fraction of a second. This rapid expansion would have set the stage for the large-scale structure we observe today, including galaxies, stars, and clusters of galaxies. By studying the cosmic microwave background, CMB radiation, which is the afterglow of the Big Bang, scientists can learn more about the universe's early moments and the forces that shaped its expansion. Telescopes like the Planck satellite launched by ESA have provided detailed measurements of the CMB, helping to refine our models of the universe's early evolution. The study of cosmic inflation is also essential for understanding the potential boundaries of the universe. If the universe underwent a period of rapid expansion, it may have erased any initial edges or boundaries, creating a universe that appears infinite on large scales. The ongoing efforts to study these early moments and the forces that shape the universe could ultimately help us understand whether the universe is finite or infinite, and how the boundaries of space, if they exist, might be defined. In addition to these large-scale projects, the future of cosmology holds immense promise, as new discoveries continue to challenge our understanding of space's extent. Advances in observational technology, both on Earth and in space, will allow us to study the universe in greater detail, potentially revealing new information about its structure and its limits. For example, the study of gravitational waves, ripples in space-time caused by violent cosmic events, has opened up a new window into the universe's most extreme phenomena, such as black holes and neutron stars. By studying gravitational waves, we can learn more about the fundamental nature of space-time itself, and perhaps uncover new insights into the boundaries of the universe. Additionally, the development of more powerful telescopes, both on the ground and in space, will continue to push the limits of our observational capabilities. The extremely large telescope, currently under construction in Chile, will have a mirror over 40 meters across, making it one of the largest optical telescopes in the world. It will allow scientists to study objects billions of light-years away with unprecedented detail. As we continue to develop better tools for exploring the universe, we will get closer to understanding the true nature of space and its boundaries, whether they are real or whether space stretches on infinitely, beyond the limits of our observation. The future of cosmology holds exciting possibilities for reshaping our understanding of space and its boundaries. With the James Webb Space Telescope and other advanced observatories, we will likely uncover new insights into the farthest reaches of the universe. The Large Hadron Collider's exploration of fundamental forces and the study of cosmic inflation will continue to shed light on the deepest mysteries of the cosmos. And as new technologies and discoveries emerge, we may find that our understanding of space and time is more fluid and complex than we ever imagined. Ultimately, these efforts aim to answer some of the most profound questions in science. What lies at the edge of the observable universe? Is the universe infinite, or is it finite, with boundaries that we're only beginning to understand? With each new discovery, we come one step closer to uncovering the truth about the universe's extent, and perhaps, in the process, uncovering truths about the very nature of space itself. As we've journeyed through the vastness of space, we've encountered some of the most profound questions humanity has ever asked. From the early musings of ancient philosophers to the cutting-edge theories of modern cosmologists, we've explored the boundaries of space and time, concepts that seem as limitless as the universe itself. We've delved into the nature of space, from classical notions of an infinite expanse to the mind-bending ideas of curved space, multiple dimensions, and even the possibility of parallel universes. Each of these theories, while fascinating, opens up even more mysteries about the true extent of space. As we stand on the shoulders of giants, scientists like Albert Einstein, Kurt Gödel, and Roger Penrose, we're confronted with the reality that the universe's boundaries may remain elusive. Despite all the advancements in telescopes, particle accelerators, and quantum mechanics, the ultimate edge of space might be something forever beyond our reach. Whether space is infinite or finite, whether it has an edge, or whether the universe loops back on itself, we may never fully grasp its true nature. What we can say, however, is that the universe is far stranger and more complex than we ever imagined, and every new discovery only deepens the mystery. In exploring these ideas, we've encountered a fascinating interplay between science and speculation. Theoretical models, from the spherical universe proposed by Jean-Pierre Luminet to the speculative musings of David Deutsch on the universe as a mathematical construct, have pushed the boundaries of our understanding. These speculative theories, though not yet proven, are part of what drives the pursuit of knowledge. They challenge our assumptions and encourage us to think beyond the limits of what is currently observable. Perhaps that's the most exciting aspect of this journey, the realization that our understanding is always evolving, and that the answers we seek might lie in places we haven't even thought to look yet. So, as we conclude this exploration of space's boundaries, the mystery remains. The universe is vast, and its true extent may always be beyond our grasp. But the journey to understand it, the questions we ask, and the theories we develop along the way are part of what makes our exploration of the cosmos so exciting. And perhaps, as we continue to probe deeper into the nature of space, we'll find that it's the very mystery of the universe that fuels our endless curiosity. Keep pondering, keep questioning, and never stop exploring the infinite complexity of the cosmos. After all, the universe might just have more surprises in store than we can imagine.